Hi, my name is Telen. I am a postdoc researcher in the nonlinear algebra group at our Max Planck Institute for Mathematics in the Sciences, and I will tell you about a project entitled Likelihood Equations and Scattering Amplitudes. This is joint work with Bernd Sturmfels, who is the head of our research group. I'll start by situating our work a little bit. So as the title suggests, it's going to be a mix between statistics and physics. And this all started out basically by Bernd, whose picture you see here in the slide, pointing out to me that a very important problem from particle physics is strongly related to a central problem in algebraic statistics. And we'll get to this problem later, but I can already tell you now that in order to solve it, you need to solve a system of algebraic equations. And since this was the topic of my PhD, this is where I come in. So our aim in this project is twofold. On the one hand, we want to use the expertise that we have in the nonlinear algebra group in the domains of algebraic statistics and solving systems of equations to solve challenging problems from particle physics. And on the other hand, we also want to use the insights that the physicists have in these equations to hopefully trigger advances in algebraic statistics and in solving equations. Our preprint is on the archive, and you're of course kindly invited to have a look. Okay, so let me say a few words about likelihood equations in algebraic statistics. The setting is as follows. We are considering a discrete random variable with n+1 states. So probability distributions for such a random variable, they live in the probability simplex, that's this set delta n here. And it consists of all points in a real n-dimensional projective space whose homogeneous coordinates all have the same sign. And then for us, a statistical model called X is a subvariety of this real projective space that intersects this simplex. And this is usually the convention in algebraic statistics. In fact, I've already shown you an example of such a model. On the background of my title slide, I had the logo of our Max Planck Institute, and this represents a statistical model inside of the three-dimensional probability simplex. So this is this three-dimensional probability simplex, and inside of it, you have this curly thing representing the model X. Okay, now suppose that you do an experiment and that you observe state I a total number of Si times. Then it's a very important question in statistics, what is a probability distribution inside of our model that best explains these data that we observed? Okay. So I will repeat that question at the top of the next slide. And one possible answer coming from likelihood inference says, well, in order to find that probability distribution, what you need to do is maximize the likelihood function L on the model X. Okay, so we need to maximize this likelihood function, that's a rational function in the PIs on our model X. Now note that given a certain probability distribution P0 up to Pn, this likelihood function represents the probability of making the observation S0 up to Sn. So maximizing this likelihood function has the natural interpretation of finding the probability distribution for which your observation was most likely. Okay, now since we're working on the real part and the positive part of a projective space, this is equivalent to maximizing the logarithm of this function. So if we take the logarithm of the likelihood function, we obtain this function uppercase L, which is called the log likelihood function, and it looks like sum of Si log Pi minus the sample size times the logarithm of the sum of the Pi. So instead of maximizing the likelihood function, we'll be maximizing the log likelihood function on our model X. Okay. Now in this presentation, the model X is going to come in the form of a parametrization. So that means that we have these parameterizing functions P0 up to Pn, depending on X, and X is a point in a d-dimensional real parameter space. And if this is the case, then to find the maximizer of this log likelihood function, we solve these equations obtained by taking the partial derivatives of our log likelihood function with respect to all the variables. So these are called the critical point equations of L. They're also called the likelihood equations of our statistical model X. Okay, now in a statistical context, it makes a lot of sense to ask that these functions pi sum to 1 because they represent probabilities. And if this is the case, then you don't need to worry about the denominator in the likelihood function or about this last term in the log likelihood function. Okay, let's do an example. So the statistical model that I want to consider is the space M06. So X is M06 in this example. This is the moduli space of genus 0 curves with 6 marked points. Now, if you're not familiar with moduli spaces, you can think of this as the open Grassmannian of lines in P5, modulo its 6-dimensional torus action. And this variety sits in P8 via the parameterization given by these Qij functions here, where Qij is the ij minor of this very nice 2x6 matrix. So for instance, Q35 would be the determinant of the columns 3 and 5 in this matrix. So that would give x3 minus x1. Okay, now as I said before, we would like these parameterizing functions to sum to 1. So to that end, we scale these functions Qij by these constants alpha ij to obtain the Pij's. And in this way, we obtain a statistical model with n plus 1 equals 9 states. And the model is parameterized by these affine linear functions Pij, depending on our parameters x1, x2, and x3. Note, for instance, that P35 is Q35 times 1 over 9. That means alpha 35 would be 1 over 9. Okay, so now we do an experiment and we obtain some data Sij, and what we need to do is compute the critical points of the log likelihood function L, which is the sum of Sij log Pij. And I just want to point out that this log likelihood function is the same as the sum of Sij log Qij up to this constant term C, which comes from the scaling by our alpha ij's. And it'll become clear in a slide or two why this is relevant. Okay, so we plug in some positive integer data Sij and compute the solutions to the likelihood equations. And I found 6 solutions and I listed them here. So the first solution carrying the hat in the notation corresponds to the maximum likelihood estimate. That means if I take the first solution and I send it through the parameterization, then I obtain the probability distribution Pij that best explains the data Sij that I plugged in. Okay, so you can check that these numbers sum to 1. The other 5 solutions are also critical points of the log likelihood function, but it turns out if we send them through the parameterization, then we don't land in the probability simplex. So this means the first solution is the statistically relevant solution here. Okay, so the reason I'm showing you these numbers is they satisfy some remarkable properties. So first of all, note that all the solutions are real. So the methods that we use for solving these equations are particularly fit for solving over the complex numbers. So in fact, I looked for all complex solutions to these likelihood equations, and it turns out all of them are real. And they're the 6 solutions shown here. Moreover, there is exactly one solution for each permutation I, j, k of 3 indices 1, 2, 3. So that works as follows. For each such a permutation, there is exactly one solution satisfying this chain of inequalities. So for instance, the first solution here satisfies x1 is smaller than x2 is smaller than x3. For the second one, we have x1 is smaller than x3, smaller than x2, right? And so on. Okay, now it turns out these chains of inequalities are the defining inequalities for certain bounded regions in R3. And these are the bounded regions in an arrangement of planes defined by our functions Pij. So remember, the Pij's are affine linear functions of the parameters x1, x2, x3. So each of them defines a plane in R3. And this arrangement of 9 planes cuts out exactly 6 bounded regions given by these inequalities here, and each containing exactly one solution to the likelihood equations. Okay, So how do we link this all back to physics? Well, the sort of experimental setup that we have to keep in mind for this is the following. So we're thinking of a black box represented by the black disk here in the slide, in which we send 3 particles. So the 3 arrows on the left, they represent 3 incoming particles which enter this black box. They interact inside of this black box, so something happens, and out come these 3 new particles, particles number 4, 5, and 6. The vectors k1, k2 up to k6 are the momentum vectors associated to these particles. So they capture some of the physical information that we want to keep track of regarding these particles in this process. So such a process in which particles enter this black box and they interact and new particles come out is called a scattering process. And to such a scattering process, the physicists associate a potential function, which is called S here in my slide. This is the sum of Sij log Qij, where the Qij are exactly the Qijs we saw before. So they are these minors of this nice 2×6 matrix. And here the Sijs are the Mandelstam invariants. So these are kinematic invariants associated to this scattering process. And for instance, Sij is obtained by taking the sum of momentum vectors ki and kj, and then taking the Minkowski inner product of the result with itself. So that's what this square stands for. Okay, so we have this potential function, and if we take the critical point equations of this potential function, so obtained by taking all of its partial derivatives and equating them to 0, then we obtain the scattering equations associated to this scattering process. So because there are 6 particles involved, they are called here the 6-point scattering equations, and they are the critical point equations of this potential function. Now, by what I said a few minutes ago, we know that this potential function is up to some constant term, the same as our log likelihood function. So that means that these two have the same critical point equations, and we conclude that the likelihood equations for this moduli space M06 as a statistical model are exactly the 6-point scattering equations. If you want to learn more about these scattering equations, you can consult this paper by Cachasso-He and Yuan, in which they introduce them as well as their connection to scattering amplitudes, which I will talk a bit more about later. Okay, now you can imagine that in general you'd like to consider scattering processes involving more particles. So the m-point scattering equations will be a system of rational function equations obtained by taking the critical point equations of a log likelihood function L. And here the model is the space M0M. So this is the moduli space of genus 0 curves with M marked points. That has dimension m-3, so there are m-3 partial derivatives. And for positive data, there are m-3 factorial real solutions. And again, each of these real solutions will be contained in some bounded region in R to the m-3. And these bounded regions are the bounded regions in an arrangement of hyperplanes given by the parametrizing functions for M0M. And this is all a consequence of a theorem that's known in algebraic statistics as Varshenko's theorem. Now, one of the punchlines in our paper is that recent methods from numerical algebraic geometry allow us to solve these scattering equations in a very efficient and reliable way. And moreover, these methods are implemented and they're available in off-the-shelf software, so you can really do this at home. And we chose to use homotopy continuation.jl, which is a relatively recent Julia package for doing homotopy computations. I want to show you some computational results. So we solved these scattering equations for m equals 10 up to 13 particles. This gives statistical models with n+1 states, which ranges from 35 to 65. Number of solutions is m-3 factorial, so that goes from about 5,000 to about 3.6 million. And the last column here corresponds to computation times. So as you can see, we computed all 3.6 million solutions for m equals 13 in less than 10 minutes. And I just used my own laptop for this. There are no supercomputers involved. So this is really highly effective. Okay, so in the last part of my talk, I want to say a few words about scattering amplitudes. So we're considering this scattering process, which in general involves m particles, and I'm showing the picture for m equals 6 here again. And to such a scattering process, we associate a function a called the amplitude, or the scattering amplitude associated to this process. So this function a is given by this limit of this integral, and the expression looks a bit complicated, but let's parse it for a second. So we're taking the limit for epsilon going to 0 of epsilon raised to the power m minus 3, and here m minus 3 is the dimension of our associated moduli space. The integral is over the positive orthant in r to the m minus 3. In the integrand we have the product of the qij's raised to the power sij, and here the qij's are almost like the qij's we were using before, except I obtained them from a slightly different parameterization of the moduli space, but I won't go into these details. This is all raised to the power epsilon, and in the denominator I have the product of my parameters x1 up to xm minus 3. So note that the x's are integrated out, and we're taking a limit for epsilon going to 0. So that means what's left is a function of these Mandelstam invariants Sij. So the amplitude is a function of the Mandelstam invariants Sij. In general, this is a complex valued function. And the reason why this is so important for the physicist is that the modulus squared of this amplitude function has the interpretation of a probability density function. So that means that the modulus squared of this amplitude function tells us what to expect for the outcome of a certain scattering process. And it's a really important problem to understand the mathematical properties of this function a, as well as to evaluate it. Okay, so we can evaluate this amplitude a for m equals 6. And it turns out, quite surprisingly, that the amplitude evaluates to this very nice rational function in the Mandelstam invariance, where I used this short notation Sijk for Sij plus Sjk plus Sik. So there's 14 terms, and each of them looks very, very simple. And in general, also for more particles, the amplitude has a very nice combinatorial description. Perhaps an even more surprising expression for this amplitude is a sum over the critical points of our log likelihood function L. Okay, so what you need to do is evaluate the determinant of the toric Hessian matrix H sub L in the critical points and sum the reciprocals. So this relates the solutions to the scattering equations to the amplitude. And this is one of the main reasons for the high interest in these scattering equations. Now we would like to link this back to algebraic statistics. And what we note in our paper is that, like for the moduli space M0M, there are certain other statistical models that admit a natural amplitude. So our definition for the statistical amplitude, or the amplitude of a statistical model X, will be the limit for epsilon going to 0 of epsilon raised to the power d, and here d is the dimension of the model X. We're integrating over the positive orthant in Rd. In the integrand, we have the likelihood function L raised to the power epsilon, and in the denominator, I need to take the product of the variables. And let me just go back to the previous slide to show the similarities. So here also the blue part in this integral is exactly the likelihood function for the moduli space M0M as a statistical model. So this is how we generalize it for other models. Now, when do we call this amplitude natural? So first of all, the models for which we call this amplitude natural are defined to be positive models in our paper. And we call these amplitudes natural because for these positive models, this expression fits into the framework of stringy canonical forms introduced by Arkani-Hamed, He, and Lam. And because we have the machinery of this framework, we can again show that we have this similar expression for the amplitude as a sum over the critical points of the log likelihood function, which relates the solutions to the likelihood equations to statistical amplitudes. And just as a teaser, I want to say that one of the reasons why we think this is exciting is that these expressions for the amplitude look a lot like marginal likelihood integrals in Bayesian statistics. So we see this as a first step of linking the solutions to the likelihood equations to marginal likelihood integrals. Okay, let me wrap up by reiterating that we have used methods from algebraic statistics and solving systems of equations to solve very challenging problems from particle physics that had not been solved before. And we also used the insights from the physicists to define positive models and their statistical amplitudes. Now, to give an outlook, some ideas for future research is the further exploration of the role of amplitudes in Bayesian statistics, as I pointed out. And there's also some work to do in using the insights of the physicists for likelihood type equation solving. Thanks for your attention.